Electric circuits. Describe the configuration of a working circuit. Explain how current can be turned on or off in a circuit and how electrical devices can be connected in a circuit. Describe the characteristics of a series circuit. Describe the characteristics of a parallel circuit. Interpret circuit diagrams. Determine the equivalent resistance of circuits having two or more resistors. Explain the cause and prevention of overloading household circuits. The big idea. Along any path which electrons can flow is a circuit. Mechanical things seem to be easier to figure out for most people than electrical things. Maybe this is because most people have had experience playing with blocks and mechanical toys when they were children. If you are among the many who have had far less direct experience with the inner workings of electric devices than with mechanical gadgets, you are encouraged to put extra effort into the laboratory part of this course. You'll find hands-on laboratory experience aids your understanding of electric circuits. The experience can be a lot of fun, too. What does it take to light a light bulb? Try to light a light bulb with just a battery and a simple piece of wire. Now try to get the same result with different arrangements of the wire, the battery, and the light bulb. Analyze and conclude. Observing. Describe both successful and unsuccessful attempts to light a light bulb. 2. Predicting. How many possible arrangements of the wire, the battery, and the light bulb will result in the bulb being lit? Making generalizations. What conditions are necessary in order for the bulb to light? 35.1. Battery and a bulb. Take apart an ordinary flashlight like the one shown in figure 35.1. If you don't have any spare pieces of wire around, cut some strips from some aluminum foil that you probably have in one of your kitchen drawers. Try to light up the bulb using the battery and a couple of pieces of wire or foil. Some of the ways you can light the bulb and some of the ways you can't light the bulb are shown in figure 35.2. The important thing to note is that there must be a complete path or circuit that includes the bulb filament and that runs from the positive terminal at the top of the battery to the negative terminal, which is the bottom of the battery. Figure 35.1, a flashlight consists of a reflector cap, a light bulb, batteries, and a barrel-shaped housing with a switch. 35.2, A, unsuccessful ways to light a bulb. B, successful ways to light a bulb. Electrons flow from the negative part of the battery through the wire or foil to the side or bottom of the bulb, through the filament inside the bulb, and out the bottom or side, and through the other piece of wire or foil to the positive part of the battery. The current then passes through the interior of the battery to complete the circuit. The flow of charge in a circuit is very much like the flow of water in a closed system of pipes. In a flashlight, or for the setup shown in figure 35.2b, the battery is analogous to a pump. The wires are analogous to the pipes, and the bulb is analogous to any device that operates when the water is flowing. When a valve in the line is opened and the pump is operating, water already in the pipes start flowing. In a flashlight, when the switch is turned on to complete the electric circuit, the mobile conduction electrons already in the wires and the filament begin to drift through the circuit. Notes: filament resistance in a 120 volt 60 watt bulb increases about 15 times from room temperature to its nearby 3000 K operating temperature in a time of about 100 milliseconds. The initial 10 amp current drawn quickly decreases to a steady 0.7 amps. Figure 35.3, electrons do not pile up inside a bulb, but instead flow through its filaments. The water flows through the pump, and the electrons, in effect, flow through the battery. Neither the water nor the electrons squash up and concentrate in certain places. They flow continuously around a loop or circuit. Concept check. What happens to the mobile conduction electrons when you turn on a flashlight? 35.2, electric circuits. Any path along which electrons can flow is a circuit. For a continuous flow of electrons, there must be a complete circuit with no gaps. A gap is usually provided by an electric switch that can be opened or closed to either cut off or allow electron flow. The water analogy is quite useful for gaining a conceptual understanding of electric circuits, but it does have some limitations. An important one is that a break in a water pipe results in water spilling from the circuit, whereas a break in an electric circuit results in a complete stop in the flow of electricity. Another difference has to do with turning current off and on. When you close an electrical switch that connects the circuit, you allow current to flow in much the same way as you allow water to flow by opening a faucet. Opening a switch stops the flow of electricity. An electric circuit must be closed for electricity to flow. Opening a water faucet, on the other hand, starts the flow of water. Despite these and other differences, thinking of electric current in terms of water current is a helpful way to study electric circuits. Most circuits have more than one device that receives electrical energy. These devices are commonly connected in a circuit in one of two ways, series or parallel. When connected in series, the devices in a circuit form a single pathway for electron flow between the terminals of the battery, generator, or wall socket, which is simply an extension of these terminals. When connected in parallel, the devices in a circuit form branches, each of which is a separate path for the flow of electrons. Both series and parallel connections have their own distinctive characteristic. This chapter briefly treats circuits with these two types of connections. Notes: after failing more than 6,000 times before perfecting the first electric light bulb, Thomas Edison stated that his trials were not failures because he successfully discovered 6,000 ways that don't work. Concept check. How can a circuit achieve a continuous flow of electrons? 35.3, series circuit. Figure 35.4 shows three lamps connected in series with a battery. This is an example of a simple series circuit, or circuit in which devices are arranged so that charge flows through each in turn. When the switch is closed, a current exists almost immediately in all three lamps. The current does not pile up in any lamp, but flows through each lamp. Electrons in all parts of the circuit begin to move at once. Some electrons move away from the negative terminal of the battery, some move towards the positive terminal, and some move through the filament of each lamp. Eventually, the electrons move all the way around the circuit. Figure 35.4, in a simple series circuit, a 9-volt battery provides 3 volts across each lamp. Think, what happens to the light intensity of each lamp in a series circuit when more lamps are added to the circuit? The addition of more lamps results in a greater circuit resistance. This decreases the current in the circuit and in each lamp, which causes dimming of the lamps. A break anywhere in the path results in an open circuit and the flow of electrons ceases. Burning out one of the lamp filaments or simply opening the switch could cause such a break. The circuit shown in figure 35.4 illustrates the following important characteristics of series connections. Electric current has but a single pathway through the circuit. This means that the current passing through each electric device is the same. This current is resisted by the resistance of the first device, the resistance of the second, and the third also, so that the total resistance to the current in the circuit is the sum of the individual resistances along the circuit path. 3. The current in the circuit is numerically equal to the voltage supplied by the source divided by the total resistance of the circuit. This is Ohm's law. 4. Ohm's law also applies separately to each device. The voltage drop or potential difference across each device depends directly on its resistance. This follows from the fact that more energy is used to move a unit of charge through a large resistance than through a small resistance. 5. The total voltage impressed across a series circuit divides among the individual electric devices in the circuit so that the sum of the voltage drops across the individual devices is equal to the total voltage supplied by the source. This follows from the fact that the amount of energy used to move each unit of charge through the entire circuit equals the sum of the energies used to move that unit of charge through each of the electrical devices in the circuit. It is easy to see the main disadvantage of a series circuit. If one device fails in a series circuit, current in the whole circuit ceases and none of the devices will work. Some cheap party lights are connected in series. When one lamp burns out, it's fun and games or frustration trying to find which bulb to replace. Most circuits are wired so that it is possible to operate electric devices independently of each other. In your home, for example, a lamp can be turned on or off without affecting the operation of the other lamps or electric devices. This is because these devices are connected not in series but in parallel to one another. Concept check. What happens to current in other lamps if one lamp is a series circuit blows out? Notes: a series circuit is like a single lane road with no alternative path. If there is a roadblock or cave-in, traffic will stop. Look at the circuit shown in figure 35.4. If the current through one of the bulbs is 1 amp, can you tell what the current is through each of the other two bulbs? If the voltage across bulb 1 is 2 volts and across bulb 2 is 4 volts, what is the voltage across bulb 3? Yes, it is 1 amp. The same current passes through every part of the series circuit. The voltage across B3 is 3 volts. Each coulomb of charge flowing in the wire from the battery has 9 joules of electrical potential energy. 9 volts equals 9 joules per coulomb. That energized coulomb of charge must distribute its energy among 3 bulbs in proportion to their resistance and return to the battery with 0 joules. If it spends 2 joules in one bulb and 4 joules in another, it must spend 3 joules in the last bulb. 3 joules per coulomb equals 3 volts. 35.4 Parallel circuits. Figure 35.5 shows 3 lamps connected to the same 2 points A and B. In a parallel circuit, each electric device is connected to the same 2 points of the circuit. Notice that each lamp has its own path from one terminal of the battery to the other. There are 3 separate pathways for current, one through each lamp. In contrast to a series circuit, the current in one lamp does not pass through the other lamps. Also, unlike lamps connected in series, a parallel circuit is completed whether all, two, or only one lamp is lit. Figure 35.5. In this simple parallel circuit, a 9-volt battery provides 9 volts across each lamp. In a parallel circuit, each device operates independent of the other devices. A break in any one path does not interrupt the flow of charge in the other paths. The circuit shown in figure 35.5 illustrates the following major characteristics of parallel connections. 1. Each device connects the same 2 points, A and B, of the circuit. The voltage is therefore the same across each device. 2. The total current in the circuit, that is, the total current through the battery, divides among the parallel branches. Current passes more readily into devices of low resistance, so the amount of current in each branch is inversely proportional to the resistance of the branch. Ohm's law applies separately to each branch. 3. The total current in the circuit equals the sum of the currents in its parallel branches. 4. As the number of parallel branches is increased, the total current through the battery increases. From the battery's perspective, the overall resistance of the circuit is decreased. This means the overall resistance of the circuit is less than the resistance of any one of its branches. Concept check. What happens if one device in a parallel circuit fails? And now a cartoon. Parallel circuit. I'm going to extend the terminals of the 12-volt battery with a pair of metal rods. A lamp will glow just as bright when connected here as here. Of course, it's still across 12 volts. Now I fasten another identical lamp. What happens to the brightness of the first? Same. Same brightness because 12 volts is across each. That's what I said. Okay. And the third lamp also, same brightness. Why not? There's still 12 volts across each lamp. How does the battery know to supply 3 times as much current to 3 lamps? I know, with 3 separate paths, the battery has 1/3 the resistance between its terminals. That's why it will deliver 3 times as much current for its 12 volts. Very good. But doesn't this mean the battery is putting out 3 times as much energy as when lighting only one lamp? Yes, and you can expect the battery to wear down 3 times as fast. Think, what happens to the light intensity of each lamp in a parallel circuit when more lamps are added in parallel to the circuit? The light intensity of each lamp is unchanged as other lamps are introduced or removed, although changes of resistance and current occur for the circuit as a whole. No changes occur in any individual branch in the circuit. 35.5. Schematic diagrams. Electric circuits are frequently described by simple diagrams called schematic diagrams that are similar to those of the last 2 figures. Some of the symbols used to represent certain circuit elements are shown in figure 35.6. In a schematic diagram, resistance is shown by a zigzag line, and ideal resistance-free wires are shown with solid, straight lines. A battery is represented with a short and long parallel lines. Figure 35.6, symbols of some common circuit devices. The convention is to represent the positive terminal of the battery with a long line and negative terminal with a short line. Sometimes a 2-cell battery is represented with a pair of such lines, a 3-cell with 3, and so on. Figures 35.7a and 35.7b show schematic diagrams for circuits of figures 35.4 and 35.5. Concept check. What symbols are used to represent resistance, wires, and batteries in schematic diagrams? Figure 35.7. These schematic diagrams represent A, the circuit of figure 35.4 with 3 lamps in series. Figure 35.5 Point 4, this is a simple circuit. A 9-volt battery provides 3 volts across each lamp. All right, so that's the circuit. That's the figure 35.4. And then next, B, the circuit of figure 35.5 with 3 lamps in parallel. And this is figure 35.5. In this simple parallel circuit, a 9-volt battery provides 9 volts across each lamp. So study that carefully. And that is figure 35.7, an extended view. 35.6, combining resistors in a compound circuit. Sometimes it is useful to know the equivalent resistance of a circuit that has several resistors in its network. The equivalent resistance is the value of the single resistor that would comprise the same load to the battery or power source. The equivalent resistance of resistors connected in series is the sum of their values. For example, the equivalent resistance of a pair of 1 ohm resistors in series is simply 2 ohms. The equivalent resistance of a pair of 1 ohm resistors in parallel is 0.5. The equivalent resistance is less because the current has twice the path width when it takes the parallel path. In a similar way, the more doors that are open in an auditorium full of people trying to exit, the less will be the resistance to their departure. The equivalent resistance for a pair of equal resistors in parallel is half the value of either resistor. Figure 35.8 shows how you can simplify schematic diagrams by using equivalent resistances. Figure 35.8a, the equivalent resistance of 2 8-ohm resistors in series is 16 ohms. B, the equivalent resistance of 2 8-ohm resistors in parallel is 4 ohms. Figure 35.9 shows a combination of 3 8-ohm resistors. The 2 resistors in parallel are equivalent to a single 4-ohm resistor, which is in series with an 8-ohm resistor and adds to produce an equivalent resistance of 12 ohms. If a 12-volt battery were connected to these resistors, can you see from Ohm's law that the current through the battery would be 1 amp? Notes: the resistance in the filament of a light bulb varies with temperature. When cold, at room temperature, it may be only 16 ohms. In a 120-volt, 60-watt bulb, while 100 milliseconds later, when it reaches its operating temperature, filament resistance increases to a steady 240 ohms. Figure 35.9, the equivalent resistance of a circuit is found by combining resistors in successive steps. In practice, it would be less, for there is resistance inside the battery as well, called the battery's internal resistance. 2 more complex combinations are broken down in successive equivalent combinations in figures 35.10 and 35.11. It's like a game. Combine resistors in series by adding, combine a pair of equal resistors in parallel by halving. The value of the single resistor left is the equivalent resistance of the combination. Notes: see note 35.6 on page 908 for more on equivalent resistances. Concept check. What is the resistance, the equivalent resistance of resistors in series of equal resistors in parallel? Figure 35.10. The equivalent resistance of the top branch is 3 ohms, which is in parallel with the 3 ohm resistance of the lower branch. The overall equivalent resistance is 1.5 ohms. Figure 35.11. Schematic diagrams for an arrangement of various electric devices. The equivalent resistance of the circuit is 10 ohms. The 60-volt battery is for numerical convenience. Most batteries are less than 60 volts. Think, what is the current in amps through the battery? neglect the internal resistance of the battery? Think. Answer. 6 amps. From Ohm's law, current equals voltage over resistance. 60 volts divided by 10 ohms is 6 amps. What is the current in amps through the pair of 10 ohm resistors through each of the 8 ohm resistors? Remember your series and parallel rules for resistors. The total resistance in the middle branch is 20 ohms. Since the voltage is 60 volts, the current equals voltage divided by resistance, which is 60 volts over 2 ohms, equals 3 amps. The current through the pair of 8 ohm resistors is 3 amps, and the current through each is 1.5 amps. The 3 amp current divides equally between these equal resistances. How much power is provided by the battery? Power equals current times voltage. Power equals 6 amps times 6 volts, which equals 360 watts. 35.7. Parallel circuits and overloading. Electric current is usually fed into the home by way of 2 lead wires called lines. These lines are very low in resistance and are connected to the wall outlets in each room. About 110 to 120 volts are impressed on these lines by the power company. This voltage is applied to appliances and other devices that are connected in parallel by plugs to these lines. As more devices are connected to the lines, more pathways are provided for current. What effect do the additional pathways produce? The answer is a lowering of the combined resistance of the circuit. Therefore, a greater amount of current occurs in the lines. Lines that carry more than a safe amount of current are said to be overloaded. The resulting heat may be sufficient to melt the insulation and start a fire. You can see how overloading occurs by considering the circuit in figure 3512. The supply line is connected to an electric toaster that draws 8 amps, to an electric heater that draws 10 amps, and to an electric lamp that draws 2 amps. When only the toaster is operating and draws 8 amps, the total line current is 8 amps. When the heater is also operating, the total line current increases to 18 amps. 8 amps to the toaster, 10 amps to the heater. If you turn on the lamp, the line current increases to 20 amps. Connecting any more devices increases the current still more. To prevent overloading in circuits, fuses or circuit breakers are connected in series along the supply line. Figure 3512, the more devices you connect to your household supply line, the more you increase the total line current. In this way, the entire line current must pass through the fuse. The safety fuse shown in figure 3513 is constructed with a wire ribbon that will heat up and melt at a given current. If the fuse is rated at 20 amps, it will pass 20 amps, but no more. A current above 20 amps will melt the fuse, which blows out and breaks the circuit. Before a blown fuse is replaced, the cause of the overloading should be determined and remedied. Often insulation that separates the wires in a circuit wears away and allows the wires to touch. This effectively shortens the path of the circuit and is called a short circuit. A short circuit draws a dangerously large current because it bypasses the normal circuit resistance. Circuits may also be protected by circuit breakers, which use metallic or bimetallic strips to open the switch. Figure 3513. Above a specified current, the metal ribbon in the safety fuse melts and breaks the circuit. Utility companies use circuit breakers to protect their lines all the way back to the generators. Circuit breakers are used instead of fuses in modern buildings because they do not have to be replaced each time the circuit is open. Instead, the switch can simply be moved back to the on position after the problem has been corrected. Notes: in practice, the lines in your home are not perfect conductors. With the large current used to operate a vacuum cleaner, the connecting wires do warm up, but for most cases, the resistance of the line can be neglected. Concept check. How can you prevent overloading in circuits? Summary: electric circuits. In a flashlight, when the switch is turned on to complete an electric circuit, the mobile conduction electrons already in the wire and filament begin to drift through the circuit. For a continuous flow of electrons, there must be a complete circuit with no gaps. If one device fails in a series circuit, current in the whole circuit ceases and none of the devices will work. In a parallel circuit, each device operates independent of the other devices. A break in any one path does not interrupt the flow of charge in the other paths. In a schematic diagram, resistance is shown by a zigzag line, and ideal resistance-free wires are shown with solid, straight lines. The equivalent resistance of resistors connected in series is the sum of their values. The equivalent resistance of a pair of equal resistors in parallel is half the value of either resistor. To prevent overloading, fuses or circuit breakers are connected in series along the supply line.